In this video, we are continuing our section on trig integrals, and we are going to do some more examples. All right, so let's get right into a practice problem, which says, let's evaluate the integral of x times secant squared of x. So I want to begin by giving you a couple minutes to try this. So I want to give you 2 minutes to pause the video to try this. It's probably not going to be enough time to finish the problem, but I mostly want you to be thinking about, how do I begin? Like, what method do I use? And then try to carry that through. So pause it in 4, 3, 2, 1, and try it. All right, so hopefully you did that. Hopefully you paused it and tried it. Let us talk about it. So in this problem, one of the things I notice is we have a product of functions, x times secant squared of x. And, one of those functions is a trig function. One of them is this, polynomial function. So I'm going to do integration by parts. So I need to pick a u and I need to pick a dv. Okay, I don't think u sub is going to work for us because, maybe the most natural choices for you are like something involving the secant, perhaps. But then the derivative of that won't involve just x at all. It'll be something much more complicated. So u sub probably won't be helpful. So what should I let u be and what to let dv be? Well, I typically want to let u be something where its derivative is simpler than it. So should that be x or should that be secant squared? I think it should be x, because the derivative of x is definitely simpler than it, but the derivative of secant squared I think is a bit more complicated. It involves chain rule. So then dv is the other stuff. That'll be secant squared x dx. Okay, so du would be then 1 dx, and then v, this is also nice because the antiderivative of secant squared is nice. It's just tangent, so tangent x. So my parts here, I'll put this in a little thought bubble. And now doing these parts, we get uv, so that's x times tangent x, minus the integral of v du. So that'll be tangent x times 1 dx. Okay, so in front I have x times tangent x, and I need to now subtract away the antiderivative of tangent. So the way we did this again, this is kind of going back to our section on u sub, is rewrite tangent as sine over cosine. So sine over cosine. And now I can do a u sub to evaluate this. So I can do a u sub. So doing my u sub, I'm going to let u be cosine x. Because then du is negative sine x dx. One of the ways I know that that's going to work is because I see this derivative in the function. I see sine x in the function, exactly where it is here. It's in the numerator. It turns out if you did it the other way around, if you let u be sine, then du would involve cosine x dx. And although I do see cosine in the integral, it's in the denominator, whereas in du here, it's not in the denominator. This is in the numerator. So it won't work as nicely if I do it that way. Okay, so if I do this, one other thing I'm going to do here to be able to sub this in is, let me pull this negative sign into the integral. So I get a negative sine x dx. So if I do that, I get x tangent x. When I pull the negative sign in, that leaves me with a plus out in front. So now my numerator becomes du. The denominator is u. Now I'm ready for my antiderivative. This is x tangent x. I get plus natural log of, I'm just going to do 2 steps in one. I'm going to do my natural log and let me plug back in for the u at the same time. So cosine x, and then my plus c at the end. And we got it. We got our antiderivative. So we need an integration by parts and a u sub for this one. Sometimes that happens. Okay, let's try another practice problem. For this next one, I got the integral of sine to the 4th of x. And again for this, I first want to have you pause the video for 2 minutes to try this. One thing I will recommend before you do a pause is to flip back to our earlier videos, or if you are using the notes, flip back earlier in the notes to see if you can remind yourself, okay, what were the strategies that we talked about when we have even powers on our sines and cosines? Okay, so pause the video for 2 minutes to try it. Pause it and try it. Pause, 4, 3, 2, 1. Pause it and try it. Okay, so hopefully you did that. Hopefully you paused it and tried it. So when we have just a sine or just a cosine to an even power, our strategies flipping back up here said, well, use these half angle identities. So like cosine squared equals this, or sine squared equals this. Okay, so I'm going to try to use those. For my problem, I have sine to the fourth though. So I can rewrite sine to the fourth as sine squared getting squared. And now let's plug in for what that inner sine squared is. So I would get this integral, big old thing getting squared. And let's plug in for what sine squared is, which is it's 1 minus cosine of 2x all over 2. And then I got that dx. So, okay, I'm squaring this whole fraction. Let's expand that. If I expand that, I get 1 minus 2 cosine of 2x plus cosine squared of 2x. And then my denominator, when I square that, I get 4. And then dx at the end. Okay, so I have this fraction. And I notice that some of the terms in the fraction, we know how to do the antiderivative of. Like I know how to do the antiderivative of 1. And even this next one is not too bad. The third one has this cosine squared, which is a bit more complicated. So first what I'm going to do is, well, I'm dividing by 4. I can just pull that 4 in front because it's a constant dividing my function. When I do that, I get 1 over 4 in front. 1 over 4 times the integral of 1 minus 2 cosine of 2x. And then plus cosine squared of 2x dx. So we know how to do the antiderivative of 1 and of cosine of 2x. Cosine squared, well, for that, I'm going to need those half angle identities again. So what was the identity for cosine squared of x? It was this. So if I'm plugging in 2x here instead of just x, now I'm going to let x equal 2x on this side. So over here, instead of 2 times x, I'll get 2 times 2x. So it'll become cosine of 4x on the right. Okay, so if I rewrite what I have here, this cosine squared of 2x becomes 1 plus cosine of 4x all over 2. Which I can rewrite that as, I can split that up further as 1/2 plus 1/2 times cosine of 4x. Because now I have some like terms that I can combine. There's this 1 in the integral, which can get added to this 1/2. Okay, and now I'm ready to do this antiderivative. I got that 1/4 in front. I'm going to put a big old bracket. The 1 added to 1/2 is 3/2. So that antiderivative is 3/2 times x. Then for my antiderivative of this 2 cosine of 2x, that'll be minus sine of 2x. I'd encourage you to just double check that by doing its derivative and making sure you get this. And then finally, there's this last term here. For that antiderivative, you got that plus 1/2 in front. The antiderivative of cosine of 4x, I know I'll have a sine of 4x because the antiderivative of cosine is sine. But I'll have to put a 1 over 4 in front because if I were to do the derivative of sine of 4x, I get cosine of 4x times the derivative of the inside, which pops out of 4. And I need this 1 over 4 in front to cancel that out. Okay, so I got my antiderivative, close the bracket. This is an indefinite integral, so I need a plus e at the end. And we got it. And we got it. Okay. Okay, so we're definitely doing some tougher examples here. So we needed to write sine to the fourth as sine squared, that whole thing squared, and then use our half angle identity for sine squared. Once we did that, we expanded the whole thing. We did some algebra. Later, we needed to use that half angle identity again. And then finally, we were able to get pieces that we knew how to do the antiderivative of. Okay, so let's end this video with one final example. And this one's going to be a different flavor of examples because it turns out it's going to involve a method that we haven't really seen in the context of trig functions, although we have seen it before, in calculus. So I got this integral of dx over cosine of x minus 1. Okay, so I'm going to get us started here before I give you a chance to pause it and try it. It turns out when you have something like a cosine x minus 1 or like a sine x minus 1, one technique we can try to do is multiply by the conjugate on the top and on the bottom. So with the conjugate, you keep this thing as it is, and you change this sign from a minus to a plus. So I'll get cosine of x plus 1, and you get cosine of x plus 1. And we'll see why this is useful after we multiply it out. So after we do that multiplication, on the numerator, technically in this numerator, there's a 1 next to this dx. So 1 times that cosine x plus 1 is cosine x plus 1. On the denominator, when you multiply these two things out, when you expand them, we will get cosine squared x, and then minus 1 squared, which is 1. So I can just write 1. And then let me move the dx to the end of the fraction. Okay, and now something very nice happens. So multiplying by this conjugate, when I have a cosine x minus 1 or a cosine x or sine x minus 1, will give me something like this, a cosine squared minus 1. And I have a trig identity for that. This just becomes negative sine squared x. And that's why multiplying by this conjugate was really nice when I have a cosine x minus 1 or a sine x minus 1. At this point, I have an integral that's much easier to handle. So here's where I want to have you pause the video to try this. Pause it for 2 minutes to try this. Again, it's probably not going to be enough time to finish the problem, but I mostly want you to be thinking about, what's the key idea? How do I begin? And what indicates to me that that's how I begin? So pause it and try it. Pause it in 4, 3, 2, 1, try it. Okay, so let's bring it back together now and talk about it. So next up, I can split up this integral into pieces. So I will split it up to get cosine x over that negative sine squared. Let me move the negative in front of the whole fraction, and then sine squared. And then for that next fraction, I'll get minus 1 in front all over sine squared. And then dx, of course. Okay, so this becomes, I got this, let's see, 1 over sine squared, that's just cosecant squared. And now I have these two different things. I have this fraction, and then I have a cosecant squared. Can I figure out the antiderivative of both of those? So yeah, for this first one, for this fraction, we can do a u sub on this. For cosecant squared, we want to recall that, so we actually know this antiderivative because we know a function whose derivative is cosecant squared. The derivative of what is cosecant squared? Well, it turns out the derivative of cotangent is negative cosecant squared. So that means if I just want to get cosecant squared, I would have to do the derivative of negative cotangent. Okay, so this cosecant squared, we're going to be able to handle. Let's split up this integral into 2. So I can do each one now. So I'll get the integral of this negative cosine x all over sine squared x dx, and then minus the integral of that cosecant squared x dx. So the second one we now know how to do. For the first one, let's do a u sub, which I can do on the side. Let's do u being equal to the sine x, the thing on the denominator. Because then du is cosine x dx, and I see that in the integral. So when I do that u sub on the integral, we'll get negative. The whole numerator becomes du. The bottom becomes u squared. And then for my next one, there's that minus in front. Now I know the antiderivative cosecant squared is going to be negative cotangent. This is an indefinite integral when I started, so I'll put that plus c at the end. Okay. For this integral, yeah, I can bring that u squared up to the top. That'll give me a negative u to the negative 2. When I do my reverse power rule on this, we are going to get u to the negative 1. So u to the negative 1, that next term becomes plus cotangent x plus c. So I'm going to rewrite u to the negative 1 as 1 over u, and then plug back in for u. So doing that, I get, that'll be 1 over sine, which is the same thing as writing cosecant x. So I get cosecant x, and then plus cotangent x, and then my plus c at the end. And we got it. We got our antiderivative.